Yeah. Welcome, everybody. I don't know if you remember November 22nd, November 30th, 2022, as well as I do. This was the day that ChatGPT was released, and I think when everything changed. And it's quite amazing to realize that that was not even 3 years ago. And before that and after that, I think for me, everything was completely different. At that time, I was running a large team at Meta where we had like 100 people with PhDs and in math and statistics and machine learning. And we were building models for developer productivity. And then when ChatGPT came out, we tried to give it some of the examples that we also gave to our own models and that we were proud of. And then when you realize that this generic model can do better than all these specialized models, you know something special is happening. And I'm pretty sure that everything that you've done in the past 3 years was impossible before that. And yeah, I just want to get you to remember how quick things went. But at the same time, I do think, and maybe that shows my age, and we were talking before this talk about this. It's easy when things move so fast and everything is different, is to forget your history. And as the saying goes, if you forget your history, you're doomed to repeat all the mistakes. And I lived through a previous AI hype. This was in the 80s. That was the Japanese fifth generation project. If you read the papers and articles from that time, I think they could have been written yesterday. The same promises, AI will do all our work. These machines, they built special hardware too. It was not GPUs, but it was different stuff. But there was a big difference. Right now, we're using these generic large language models. And back then, we were trying to use formal reasoning, formal planning, logic programming, functional programming. So it was a very more formalistic approach to AI. Well, I was back then, I was doing my PhD, and I was doing my PhD in AI, trying to do natural language processing. And the idea was if we get a lot of data, natural language data from newspapers, from books, whatever, think Anna's archive from the 80s. And if we write parsers for all these natural languages, then once we can parse these languages, now we have knowledge. Then we can translate between English and Dutch and French, whatever, and we can really understand language. But quickly I realized this is not going anywhere. And I feel sad for all the people smart people that did their PhDs in AI back then, because I think all of this stuff that they did is basically worthless. So I switched to programming languages instead. Programming languages are much easier than natural languages. There you can use formal methods, you can write parsers that actually work, you can analyze them, you can translate them. So I worked on that. And then in 2017, when neural nets came up, I thought, oh, maybe this is a better approach to AI. So I switched to do AI for developer productivity. When I started that, people were asking me, Erik, are you crazy? You're giving away all your teams to do something that cannot work. And guess what? Now everybody is building some agent to do coding or whatever. But what I say is that that's a solved problem. So coding, using AI to code it's a solved problem, but it's also solving the wrong problem. And hopefully that is something that, like, when you leave this talk, you will remember, right? Like, what I'm going to tell you is that you're doing everything wrong. And so now I have this kind of, like, one-person lab where I'm investigating provably safe AI, and I will talk a little bit about that. And the two things that I'm working on, it's like Universalis, that's a programming language, and Automind, that's a runtime. But the funny thing is that it's based, and my lab is called Leibniz Lab, because it's based on the ideas of Leibniz, who invented calculus. I don't think that Newton did it, but like it was Leibniz. But anyway, like that's the basis of all machine learning that we do today, of course. But also back then, like in the 16th or 17th, 18th century, he was already thinking about using machines to automate boring work. So like this is not a new idea. So even in the 80s, it was not even a new idea, right? People have been, even the ancient Greeks were thinking about, like, how can we use machines to automate human work? But anyway, as I said, what I'm going to tell you is that you are all wrong. So for example, when people strive for AGI or ASI, whatever that means, if you look at Meta, for example, Mark is paying through his nose to buy these kind of like super rock stars to chase AGI. Well, the stock price shows like how successful he is with that. But anyway, like I don't think that chasing intelligence that is like human intelligence is very useful. Sometimes I use this example. I say that you want to build a machine that can stay underwater for long times, a submarine. You're not going to model that submarine against a whale. Well, a whale is a natural thing that can dive deep underwater, so maybe we can build a whale, like jump in its beak into its stomach, like in the Bible, right? And then we can stay underwater for a long time. But that's obviously nonsense. We built like a machine that can stay underwater for a long time. And that machine is not necessarily inspired by nature. So I think trying to model intelligence like against nature, I think is nonsense. And I asked ChatGPT that, you see that, like the M dash, and it said, yes, we're basically apes that lie, cheat, steal, because we needed to survive in like a hostile world. But we as humans are not at all rational. We don't use logical thinking. We don't work optimally. So why would you want to get like model intelligence to be like humans? I think that's wrong. Here's another example. A lot of people, I think, when you, and maybe I don't know in this room, but if you read the popular press, are worried about hallucinations. Oh, I asked the model a question and it gives me a nonsense answer. Or maybe I can do prompt injection. I put like a little kind of like hidden text somewhere and now suddenly it gives like a different answer. I think those are the easy problems, right? The model follows instructions it should ignore. That's easy to solve. What is much harder to solve is the opposite problem. Say that I want to build an agent that uses Workday to kind of like enter salaries and like stock packages, and I ask it to kind of like, say, oh, base salary 100 million and like, $1 billion in equity. If you have a good chance that if you ask this to an agent, it will say, ho, 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 that is impossible. Those numbers are nonsense. I cannot do that. But as I just said, like, Meta is hiring people with those kind of pay packages. So the model should not refuse these instructions. But the problem is that a lot of models are aligned, so they're trained to get like not go like outside these boundaries. And now we've made these models kind of useless because there will be certain instructions that they will refuse to follow. And I think that is a bad thing. And again, I think I'm probably one of the few people that thinks that's the case. But another way to look at that is when you make models aligned, which means that you have them refuse to give answers to certain questions, you're introducing tree-valued logic. Because now the model can say something that's true, which is great. It can say something that's false, which is fine, because I will show you how to validate that. But it will also say, I don't know, or like, I don't want to. And this is like having tree-valued logic like in SQL. And I know that we all love tree-valued logic in SQL. But now, behind, like, you know, under the covers, behind the back door, we have reintroduced tree-valued logic into our agents because of alignment. All right, so how can we solve this problem where models give wrong answers? Well, we know how to do this in the real world. Many of you still work at companies, and if you come to this conference and you want to expense the conference fee, you have to submit an expense report. And then probably, as evidence that that is a real expense report, you have to hand in a receipt, right? Now, that is like a pattern that we use a lot. So in order to do some action, you have to also provide evidence that that action is real or true. And often, providing that evidence is harder than checking that evidence. Because for whatever administrator that looks at your expense reports, that's easy to check. Oh, like the amount on the expense report is the same as the amount on the receipt. But you had to do all the work to get the receipt, to ask to forget the receipt. This conference had to write software to be able to generate receipts. So it's an asymmetrical situation. It's much harder to create the evidence than to check the evidence. And what you see now also, that models, when you ask them a question, like who is head in the box, they provide evidence. You can check whether the answers are correct because they give you hyperlinks, citations that you can check. And sometimes they give you wrong answers with a hyperlink that you can check to see that they're wrong. I wish I had like beautiful hair like that dude. All right, so then the other thing, I think where I'm puzzled, is that people are funding and spending billions and billions of dollars to build like new foundation models, bigger models to chase this like general intelligence, where what I think is that these models are probably good enough, and what we really need is we need a new compute platform that is built on top of these models. So right now we have like Java or Python or Go or .NET. These are all compute platforms that are based on often like a virtual machine. Even Python has a VM underneath, right? And then like an ecosystem of package managers and stuff like that. And now with AI, we have a new compute paradigm. And so what we need is like new tooling and like new programming language. That's the big difference. That's the big problem, not like, you know, chasing more models. Like just with CPUs, there's like 3 or 4 CPUs that everybody uses. I think that's the same with models. We don't need 10 different models. Like just having a few companies create new models, that will be a commodity just like CPUs, and then the value is created on top. But hardly anybody is working on that. All right, so when I get like hand wave saying like, oh, these neural networks are like computers, I think the analogy is quite striking, at least for me. So if you look on the left, that's the traditional computer. And on the right is what I call the neural computer. So the weights of a neural net, that corresponds to the ROM, the read-only memory of a traditional computer. The RAM, that's your context. Now everybody is talking about context management, that's important. Well, if you're using an operating system, you have virtual memory because you don't have infinite memory, so you have to manage your memory. So that's context management. There's nothing new there. People say, oh, context management is like the hottest thing. It's like, we have been doing fucking context management since the 1950s because it's just virtual memory, all right? Instruction set, tool calling, and so on. So there's really very close correspondence to traditional computers and what I call neural computers. And the model itself really is just like a tiny part of that. It's really like the branch predictor in a CPU. What does the branch predictor do? It looks at the instructions it has executed so far, and then it predicts the next instruction. Well, that's exactly what an LLM does. Right? So an LLM is just a branch predictor in this new neural computer. Then the other thing I hear a lot is, oh, like RAG is dead, or like you only need more compute for inference. But I don't think that's right. In order to build useful things, in order to have articulate sentences, you need nouns and verbs. So you need data and you need tools. And both are equally important. If you have only one, you cannot build anything useful. So this is my vision. So what I want to build is the programming stack for the AI era. And on the left, I use .NET, but you can, of course, you can substitute Java, Python, Go, anything in there. And just like the machine has all this correspondence, this stack has also a correspondence. And there you see the Automate, that's the runtime, and Universalis is the programming language or reasoning language. We need something like a package manager to have to share code that people write. And then just like in the past, write once, run anywhere, this thing should run on different models. So prompt once, run anywhere. So this is what I'm trying to build. Whenever I try to pitch this to VCs, their eyes glaze over and they say, oh, this guy's crazy. Should I call a mental institution or something to have him admit it? But I still believe everybody's wrong except me, which is I think, maybe a sign of mental illness. I don't know. All right, let me give you another example where I think everybody is wrong. If you're a functional programming geek, and maybe there's functional programming geeks in the audience, you really is oh, look, you don't need anything. I can do everything with functions. I can even do numbers and arithmetic with functions. Look, here's church numerals. 0 is this function, and then I can do multiplication and so on. That's really cool if you're a theoretical computer scientist or a functional programming geek, but it's horrible for performance. So every computer has special purpose circuits to do arithmetic. Now, in models, you see the same thing. People are trying oh, we're going to teach these models how to do arithmetic. Oh, how cool. That's complete nonsense. Because why would you want the model to do arithmetic if we already know how to do it? You should teach the models how to use tools that do arithmetic, right? Instead of teaching the models to do useless stuff. This is as stupid as using church numerals. And now I'm not the only one that thinks this. There's this theory of the extended mind theory that says that intelligence is not just in the brain, it's really also in the tools that you use. And that's true. As I look at this beautiful building, this is part of our intelligence. By having this building and meetings like this, we can share ideas and we become smarter. So this is being here in this building is an example of extended mind theory. All right? So what I'm saying is that the models are not that important. It's using tools that's important. So and these models should just orchestrate tools. Here's another axiom that I use. And sometimes people say, oh, Erik, this is a little bit extreme, but I do believe in it, is that ultimately we will be in between the AI and its objectives, and it will kill us. And then you say, Erik, but that's a little bit extreme. But if you've ever used AI coding assistants and you have tests, and it cannot make the code to pass the tests, the model will start to kind of like reward hack. It will start to delete your tests. You must have all seen that, right? But it's the test now, tomorrow it's us. All right, so what I'm saying is that let's keep it really simple. You should never, ever trust a model, okay? Like, always assume that the models are malicious. And then you work from there, and I'll show you what we can do about that. But that's, I think, a good assumption. Like, the model is always trying to fuck you over. Excuse my word. All right? So here's another, maybe a slightly more polite way to show it. It's like, you know, like Simon Wilsonson's like trifecta. If you have untrusted content, prompt injections, private data, and ability for the model to communicate with the outside world, bad things can happen. All right? But why do bad things happen? Well, here the assumption is that it's probably the people that put the untrusted content in there, that do the prompt injections, that cause the bad thing to happen. But of course, it could also be the model, right? The model can try to, like, you know, make this happen. So, but again, here, like, you should never trust these things. These systems that we're building can do real harm. Now, one solution that seems to be in fashion is, well, then let's use another model to have, like, you know, judge the output of the previous model. Well, that's great. It's like, you know, like the fox guarding the hen house. It's like the judge kept, like, you know, being the jury. I think that's, yes, it's easy, but it's nonsense. This will lead to, like, the model, if the model is really malicious, it will, of course, like, you know, do what's good for itself and not for us humans. And now again, like looking at history, we have solved this problem, like, I don't know, like thousands of years ago. You know, you have to have separation of powers. And so not the same person should not be the judge and the jury at the same time. So this is a principle that our society uses and makes it work. So we should use the same principle for our models. Third principle that I'm using, I already mentioned this, is this separation, this asymmetry between producing evidence and checking evidence. So it's always easier to check than to prove. And this is also something we already use with CAPTCHAs, for example. Although CAPTCHAs, their use is to keep humans out, and the idea was that it was hard for machines to solve them. Things have turned around now since November 30, 2022. So what we need is the opposite of a CAPTCHA, to keep the humans out and to let the machines in. But we should only let in the machines that have good intentions. All right? So how can we do this? I have 5 minutes, so I'll give you the answer here. So how can we solve this, right? So how can we build the dual of a CAPTCHA that is like, you know, like, is not meant for humans? It's meant for machines, but it's only allowing the good machines to go through. Well, the way to do that is that the models generate an artifact that can be inspected independently. So it should be inspected not by another model, because that would be like, you know, clash of, not separation of concerns. It should be able to be validated by something externally, that artifact is safe. And then, as a side effect, we see that this also kind of like improves reasoning and uses less tokens. And people have like figured this out. These are like recent papers that kind of follow. If you have the model kind of think in code, it suddenly will kind of like think better and it will be cheaper. But I think what these guys are missing is the real benefit, namely if the model thinks in code and it produces code, you can inspect that code and you can prove properties about that code. In fact, you can prove properties to show that that code that the model produced is safe to run, it's not going to hurt you. All right, so that's kind of like, let's call it guard or whatever. And so this is the architecture of my virtual machine. So the user asks a question, and then you generate a spec in a language. That language is Universalis. So that spec is also vibe coded, right? Like I don't expect humans to write that thing, but you write the spec. But that spec is your contract between you and the model. And you sign off on that spec. And then the AI, given that spec, generates code and a proof that that code satisfies the specification, right? And doing that proof is hard. And this is why we don't prove our software except if it's like for like a nuclear reactor or something. Because proving correctness of code is really hard. But these models are really good at that. So we let them do the hard work, and then checking the proof is easy. So we have a verifier. And note that you don't need to trust the code. You don't need to trust the proof, because the verifier is not a model. The verifier is something that we trust. Right, that is something like, like lean or a theorem prover that we kind of trust. It's not another model. And then we can run it. And maybe we need to do some checks at runtime because not everything can be validated statically. Now, if you know how the JVM works or .NET works, it's not very different. This is just bytecode verification. If you load bytecode into the JVM, it verifies that this bytecode, it only checks memory safety, and then it runs it, but it also needs to do some runtime checks for array covariance, for example. So I'm not proposing something like new, it's just like, a different way to do bytecode verification. I have only 1 minute, so I need to tell people that another thing that they're wrong, Python seems to be the winner here. I love Python. It's a great language for humans. Okay, it's designed for human ergonomics. It's not designed for machines. If Python has significant white space, that messes up with token use. It's designed for machine efficiency. I don't know if you use slots or lazy imports or cinterop. These are all things that have nothing to do with AI. These are built for traditional machines. And lastly, they're designed for flexibility. So in Python, you can do monkey patching. Import can do anything. So it's impossible to reason about a Python program, to reason about its correctness. And that's why we need a new programming language. And I'll leave it at that, because I'm out of time. But my programming language is basically Prolog. It's like logic programming with natural language infused. And now your specifications are in the same language as your programs. And the model can produce these proofs. And we can use a traditional theorem prover to prove that the code is correct with the specification. So that's my talk. Oh, the boss says, okay, good. That's good. We still have humans here. So here's another thing that I think we are wrong. We often kind of become extremists. Suddenly, chat interfaces are the hype. And I think chat interfaces are great. But traditional UIs were there for a reason. Because sometimes you don't want to get type stuff in. You just want to click from a menu or click some message boxes. So what I do is I have hybrid UIs where when you communicate with the system, it might generate a traditional UI on the fly. Now this is also copied now. Other people are doing it. Claude Code also has this hybrid UI, but they do everything with text. But again, it's not a pure chat interface anymore. There's also a UI. It's just a matter of time before people say, why do we have to do these text UIs? Can't we just have real menus in there? So just wait a few months, and Claude Code will have like real menus in there. Now, the implementation of my system is also interesting. I used to have the model generate source code, or Universalis source code. But of course, these models are not trained. They don't know Universalis, so they would always generate bad code. So what I do instead, I have it generate JSON AST of the language. And with structured outputs, you just give it a schema, and now it will always generate syntactically correct code. And then I just kept like translate it into user-facing syntax. I kept like, generate Daphne for verification, and I use Kotlin for the runtime. Again, this is not a new idea. This is called intentional programming. People have been chasing this for ages as well. This will be the last thing. So one thing that I think is my biggest open problem is that if you look at traditional design by contract, these are, like if you look at Daphne, like pre-post conditions, that is meant to talk about correctness of code. But it's not really meant to talk about safety of code, and not about like, safety about like enterprise things. So to go back to the example of your expense report, if you have an agent that deals with your expense reports, you don't want that agent to commit fraud, and then you will be fired and go to jail because it got expensed like $10,000 for something that you never spent, right? So you want to be sure that this agent, when it submits an expense report, that adheres to the rules of your company with respect to expense reports. So we have to somehow express policies, like corporate policies, in such a way that we can reason about that AI can reason about that we can generate kind of like proofs of programs that they satisfy these rules. And I think that's a little bit of an unsolved problem. So I'll leave it here.